Today we're going to finish our 6.5 notes, and today we're going to focus on the factor theorem. We've already talked about dividing polynomials and different ways to do that. You can either use long division if you're dividing by a nonlinear factor. However, using synthetic division is probably the easiest way to go as long as you have a linear factor, for example, like x minus 3. And we related the results to the remainder theorem. Today we're going to talk about the factor theorem. So polynomial long division, and we experimented with doing that long division, and then we also showed how it related to synthetic division and how the remainder was always this last term, like our 15, which is also what if you had evaluated at that same x value or at that same root. So we had divided by x minus 2, which is really like substituting in x equals 2. And we got this 15, so f of 2 equals 15, but that's also, that 15 is that remainder. So when we divided our cubic polynomial here in A by the linear factor x minus 2, we got a remainder of -5. We were able to then write it as a polynomial plus some remainder. In B, however, and this is where we're going to explore a little bit more, in B we divided by a linear factor x plus 3. So really what we were doing was we were substituting in x equals -3. We got a 0 as a remainder. Now, let me remind you of some very simple division. So if I took 5 and divided it into 25, well, 5 goes into 25 5 times, leaving me with absolutely no remainder. That means that 5 is a factor of 25, right? If I made a factor tree, right, I'd be able to break it down into its factors. The same is true here. If I divide by a linear factor like x plus 3, which is the same as substituting in x equals -3, right? This is the same as saying x is equal to -3. And I get 0 as a remainder, then that tells me that x equals -3 is a root. So this is going to be a root. And therefore, x plus 3 is a factor of the polynomial. And then when I divide out that factor of x plus 3, I actually get another polynomial that then I could potentially work with. Maybe I use the quadratic formula here to get the other zeros. Maybe the other zeros aren't real, and we're going to dive into that. Okay, so that brings us to the factor theorem. The factor theorem states that if you plug some number in, such as p, so f of p equals 0, then the binomial x minus p is a factor of that polynomial. So that would mean that p, I think I have an error here, is called a 0, a root, a solution, an x-intercept of the polynomial f of x. All right, so that's our factor theorem. So let's practice that here. So we are going to factor f of x equals this cubic polynomial. We know that x equals -3 is a root because f of -3 is equal to 0. So that tells me that x equals -3 is in fact a root. So then x, if I set this equal to 0, x plus 3 would have to be a factor. All right, so I'm going to use synthetic division here. I'm going to basically factor out that factor of x plus 3 by doing synthetic division. So I'm going to make sure that every single term is accounted for. I'm going to do the coefficients 2, 11, 18, and 9. Bring down the 2, multiply. Okay, I in fact do get a 0 as my remainder. So this is going to now leave me with the polynomial 2x squared plus 5x plus 3. So the number that's to the left of the remainder, that's your constant. And then every single term increases with degree. So 5 is your linear coefficient and 2 is your quadratic coefficient. I can now set this equal to 0 and continue to try and solve it. It's a quadratic. I should be able to factor it. And if I can't factor it, I could use the quadratic formula. So let's see if we can factor this. Are there factors of 2 and 3 that I can either add or subtract that'll give me 5? Well, this makes it nice and easy. So it's either going to be 2 plus 3 to give me 5, or it's going to be 6 minus 1. So let's see what we get. Now, both signs are positive here, so that tells me something. I think it's going to be a 2 plus a 3, because everything needs to be positive to be added together. So my inners and outers here will give me a 3x and a 2x to give me 5x. So I believe this is how it should be. Set those equal to 0. I can find my other two roots. So I know that x equals -1 and x equals a -3/2. Now this is a cubic polynomial. It's got a positive leading coefficient. So just to have fun here and go a little bit further, we could graph this. Let's see, what are my zeros? I got a -3. I got a -1.5. I'll call that -3/2. I got a -1. It's got that positive leading coefficient. So I know that's going to be down on the left and up on the right. And I'm not going to get all the numbers in between right now. Oh, I also know that I have a y-intercept of a +9. Let's just pretend that's my constant. So maybe it looks something like this. And you could get way more into detail by using an input-output table. X and Y axis. All right, that's not truly part of the lesson, but that is something that we've already covered in the past, and now you're getting to see how do you find all these zeros and graph these things. All right, so let's do another one of those. I've got another cubic. I know that one of my zeros or one of my roots is x equals 2. So this is a root, which means that x minus 2, right, if I set that equal to 0, would have to be a factor. So this is a factor. Not that that's super important right now, but later on it will become more important. So I'm going to use synthetic division, and I'm doing that because I have this linear factor. Again, if I had like a quadratic or a cubic or a quartic factor, I would have to use long division. All right, so I'm going to use my synthetic division here. X equals 2 goes on the outside, making sure that every single term is accounted for. Coefficients are 1, -2, -9, and 18. So because they told me that x equals 2 is actually a 0, I know that I have to have a remainder of 0. All right, so now let's see what's left. I'm going to have, well, my constant is -9. I don't have a linear term, so I don't have just an x, but I do have an x squared. So it'll be x squared minus 9 is what's left. And you have a couple ways of solving this. One is to use square roots. However, I'm going to go ahead and factor. This is a difference of 2 squares. So I know that when I factor it, it'll be x minus 3, x plus 3, which is a sum and difference pattern. So I get x equals 3 and x equals -3. So once again, I know it's a cubic. It's down on the left. It's up on the right because my coefficient is positive. This is not part of the lesson, but just for fun, let's go ahead and let's graph it. Let's see here. really bad graph, but you're getting the idea of what's happening. Ooh, and I know that my y-intercept is 18. Okay, we'll just pretend like that's 18. Okay, so if it's going to be down on the left, up on the right, it's probably going to look something, and just pretend like I know what I'm doing, like that. Now, could I do a better job? Of course I could do a better job. I could definitely use an input-output table to find some more points in between to get a better idea of this. That gives you a general idea. All right, moving on to our geometry connection. You're given an expression for the volume of this rectangular prism. Find an expression for the missing dimension. So we know that the volume is this cubic polynomial. I also know its different roots. So I have a couple of ways that I can do this, but I think one of the best ways might be to say, hey, I know that this factor, x plus 1, is really x equals negative 1. And I know that this factor down here, x plus 5, is really a 0 or a root of x equals negative 5. I can actually divide those out. So watch this. I'm going to do synthetic division. I'm going to use my cubic polynomial. I'll write in those coefficients, and everything's accounted for, it looks like. I'll start with the negative 1, 0. Okay, and I'm going to get a remainder of 0. I better get a remainder of 0, or else it's not correct. I've done something wrong. Now, instead of writing that as a polynomial and figuring out its factors and all of that, I already have another root. I have x equals negative 5. So I'm actually just going to attach it on there. I'm going to continue my synthetic division because I've already divided out one of the roots or one of the factors. So now I'm going to use my next factor or my next root to divide that even further. Think of like a factor tree. For example, let's say I knew factors of 40 were 8 and 5. Well, I could factor that even further, right? Like 8, I can continue factoring to 2 and 4, and I can continue factoring 4 to 2 and 2. Right, and that's basically what I'm doing here is I'm getting the factors and I'm breaking them down into smaller and smaller and smaller bits of the original polynomial. So I'll bring down the 2, got a negative 10, 5 and negative 25. Okay, so watch this. So what's left here? Well, my constant is 5, and my linear term is, or my linear coefficient is 2, so my linear term is 2x. 2x plus 5 equals 0. And now I can solve that. So x will equal negative 5 halves. All right, so the missing dimension then, I need an expression. I don't just need the root, I need the factor. So actually I could have used this 2x plus 5 could be the factor. I could have also written it, now I could add that 5 halves, so I could do x plus 5 halves equals 0. Which probably the 2x plus 5 is a better expression to use. But this would also work. Find all points of intersection of the two graphs, given that one intersection occurs at x equals 1. So let's see. At x equals 1, I see this is going by 10. So at x equals 1, I've got one point of intersection. Okay, so when two graphs intersect, they are equal to each other. So the two functions will be equal wherever these two graphs are intersecting. So let's go ahead and take both of our equations, set them equal to each other, maybe get that big giant equation into standard form and start factoring. Watch this. This is going to be super cool. So x cubed minus 6x squared plus 6x plus 3 needs to equal negative x squared plus 7x minus 2. Now, wherever I solve this, whatever x values I get, those are the points of intersection. Those are the x values of intersection, okay? So I'm going to put this into standard form, and then I'm going to try and factor it. Now, if I can't factor it, Well, I already have one of my roots, and I'll be able to divide that out, break this down into a smaller polynomial that maybe then I can factor. Let's check it out. So I'm going to add x squared, subtract 7x, and add 2 to both sides. So let's see, I got to put them under the like terms here. Minus 7x and plus 2. So that makes this all equal 0. And on this other side, I've got 5, a negative x. Oh, let's see here, a negative 5x squared, and an x cubed. Okay, I don't think I can factor that. However, oh, actually, I think I could factor that. I could factor that using factor by grouping, but I'm not going to. Okay, but that would be another way that you could actually solve this, is factor by grouping. I'm going to go ahead and use our factor theorem. So I'm going to put a 1 on the outside because I know that that's a 0. I'm going to use a 1, negative 5, negative 1, positive 5. I better get a 0 here. I do. Now that leaves me with a polynomial where I have a constant, a linear, and a quadratic. So I've got x squared minus 4x minus 5 equals 0. I can factor this. Let's see here. So I'm going to have, I think, a minus 5 and a plus 1. So that leaves me with x values of x equals 5 and x equals negative 1. Let's see if that looks about right. Do they look like they intersect at x equals 5? This point here, I think so. And do they look like they intersect at x equals negative 1? I'm going to say this one right here. Yep. Okay, and if I wanted to find the corresponding y values, I could just plug these values into either one of those two equations and get the y value. It didn't ask me to do that, though. Moving on to example 5, using polynomial models. In business and economics, a function that gives the price per unit of an item in terms of the number x of units sold is called a demand function. Okay, so this is going to be kind of important as we move forward into this next problem. So accounting, you are an accountant for a manufacturer of radios, and the demand function for the radios is P equals 40 minus 4x squared. So this equation right here. Now that's the demand function, and that gives the price per unit P. So this right here is the price per unit. And X is the number of radios, so that's important, produced in millions. And it costs the company $15 to make a radio. So the cost for all the radios it makes, the cost is going to be 15x. Okay, and we know that x is the number of radios. For A, we're going to write an equation giving profit as a function of the number of radios produced. So if the price per unit that it's making for every single radio is 40 minus 4x squared, then the total price or the total profit made for all of the radios would be that price per unit times the number of radios. All right, so let's talk about profit. Profit's not really just about how much money you bring in. It's also about getting rid of all the expenses that you have. And remember, that cost was $15 per radio. So the money that we bring in is this price per unit, this demand function, times the number of radios that are sold, minus the $15 per radio times the number of radios, right? Because that's basically the cost. So I think I'll write this as X, which is the number of radios, times the money that gets brought in, minus the cost of making the radios, $15 a radio. All right, so I'm going to actually call this a profit with a capital P. I'm going to go ahead and distribute. So I get 40x minus 4x cubed minus 15x. And I'm going to write it in standard form. So my profit function will actually be negative 4x cubed plus 25x. And let's remember that this is in millions. All right, so that was A. I'll put A here. Now, the company currently produces 1.5 million radios and makes a profit of 24 million. But you would like to scale back production. What lesser number of radios could the company produce to yield the same profit? I'm going to start this off as a graph. So we know that X is the number of radios, and we know that P is the profit in millions. So I don't really know what my graph looks like, but I know that I'm not producing any negative radios. So let's just pretend it looks something like this. And I know that they currently produce 1.5. So let's pretend like 1.5 is here. And they want something less. But they still want to make a profit of 24 million. So let me just go ahead and let's pretend 24 million is here. So pretend like you have this line here. Let's pretend that 1.5 million radios gives us that profit. We want this other point right here. You have two ways of doing this. The first way is to make this y1 on your graphing calculator. And then for y2, you would plug in the 24. And then you can find that point of intersection. But you already know how to do that. So let's go ahead and let's apply our remainder theorem and our factor theorem to this problem. So for B, so I'm going to write an equation. And I am going to take the profit that I want, the 24 million, and I'm going to set it equal to the profit function. Now from there, I'm going to put this in standard form. So if I subtract 24 from both sides, and from this, I know that one solution to this would have to be where they intersect would be at x equals 1.5. So I know 1.5 is a factor or a root, and or a solution, and I'm going to go ahead and use that to simplify this. So let's see, I don't have an x squared, so I'll put a 0. All right, now I better get a 0 as a remainder or else I've done something wrong. That's going to give me negative 6. And that's going to give me a negative 9. And that's going to give me, positive 24. Okay, so now what I'm going to do is I'm going to take my polynomial that's left over. So I'm going to come up over here. I know that negative 4x squared minus 6x plus 16 will be my leftover polynomial after I divide out the root of 1.5. Now from here, I could try and factor this. So the first thing I notice is that there is a greatest common monomial, and I don't really like my a to be negative. So I'm going to factor out negative 2, leaving me with 2x squared plus 3x minus 8. Now, the remaining polynomial, that trinomial in there, is not factorable. That's okay. I can still find my other zeros by using the quadratic formula. So I know that I'm just going to use the trinomial after I factored out the greatest common monomial. A will be 2, B will be 3, and C will be negative 8. Okay, so using the quadratic formula, I can find my other roots. I'm going to find that x is equal to now negative b, negative 3 plus or minus the square root b squared, which is 3 squared minus 4 times a, which is 2, and c, which is negative 8. all over 2 times a, or 2 times 2. So we're going to have negative 3 plus or minus, and this will be 9 plus 64 all over 4. Now I don't want any negative values here, okay? So when I actually put this into my calculator, that's 73. The square root of 73 is 8.544. I am not going to do negative 3 minus 8.544. I'm just going to do the negative 3 plus 8.544, which will then give me a positive number that I can divide by 4. So we'll go negative 3 plus 8.544 ends up giving me a 5.544. Divide that by 4, and I end up with 1.386. So x is approximately 1.386. Which makes a bit of sense, right? That's a little bit less than that 1.5. So this point right here, this x value would be 1.386. And again, you could have found that on your calculator, and you can double check that on your calculator. All right, so back up to this. What lesser number of radios could the company produce to yield the exact same profit? They could make 1.386 million radios. Let's see, let's turn this into millions. 1.386, 1, 2, 3. So 1,386,000 radios.